Well, good morning, everybody, and welcome to this webinar on control design for power supplies. When I was preparing this, I had great plans of all the things I could do here, and then I immediately realized what a vast topic this is and how it's impossible to get everything included in a 1-hour webinar. So I've selected a couple of topics here. One is the analysis part and how that doesn't always work out the way we want to. And then I'm going to talk a little bit about parallel modules power supplies, because they've been important for actually quite a few decades. And not everybody is using them like they should, and not everybody is aware of the advantages that they can get from parallel modules. So let's get started. If you have questions as you go along, I'm kind of going to divide this into sections, so we'll watch out for your questions. Online with us here, we have Art Nace, who's been working with our program RidleyWorks for decades now, one of our longest users. Art is from the aerospace industry, so it's very hardware oriented. And then we have John Beecroft, who's been in power electronics just about as long as I have, about 40 years now. And then we have Denise Ridley here. So everybody is going to be answering your questions as we go along. And hope you enjoy the show here. And we're sending you all a little survey afterwards. I know these webinars tend to go a bit fast, and I'm aware of that, but there's only so much we can pack in. We'd like to do a really extended version here on some unique topics later on, so you can go at a much more measured pace, a much more learning experience. And we've asked you that in the survey, whether you want to participate in that. So that would probably be late August, early September when we try doing that. But thank you all for being here. Lots of people in the room already. That's good. Let's talk about control design. Now, this is depending on your status in life and your status in working in power electronics. If you're a student, your life is very much about equations, how to generate them, how to find some new ones, how to publish them, how to get them accepted. And you get the feeling that the world of power electronics is all about equations. And for right now in your life, that is probably true. If you go to a lot of the conferences, you'll also get that feeling. The papers are very much about equations, how they generated them, and people will put up slide after slide of how they solved this bit of math and that bit of math. And I understand that because I used to do that too. And I also found out that when you're presenting it, nobody really can they cannot possibly follow along with what you did. And the second question is whether they want to know about it, or they want to know what you actually built in terms of hardware. So a couple of years ago, we had some PhD students coming in to do some work here for an internship for the summer. And my plan for the students was to have them generate some designs and some ideas and come up with some creative things, because I can't be the one to think of new things all the time, and I wanted them to help me on it. And after a few days of doing this, one of them asked me, they said, can you give me a circuit to analyze so I can write some equations for it? I said, well, no, I want you to generate the circuits. And that I think is what industry work goes on. That resulted in a little cartoon. We ran a cartoon series for a while. So this is what you get when you're coming from as a student into a company, and you're very proud of your work and your equations, and you might get a little shock when you come into the interview process where nobody's going to ask you a lot about equations. And when you actually get into work, we don't have departments inside the company that solve equations. You're trying to get product out the door, and that's what it's all about. I mean, you're going to use the math that you've learned, you're going to use the insight that you got from solving things to hopefully create some new circuits. But that's a huge culture shift when you first arrive in industry. And I remember that well because I went through it myself. But let's talk a little bit about generating equations. And maybe this is going a little bit too far in its direction these days. I mean, you need to be aware that there are limitations to what you do when you go through so much theory. So let's start at the beginning of power electronics. And then here's a little brief history of how the modeling happened. And I was very much involved in all of this, watching it, studying it, seeing it happen, and then knowing the characters and personalities, and a lot of really good people involved in deriving the analysis of power supplies. And it all started back in 1976. And 1976 was when Dr. Slobodan Chuk published his state space averaging dissertation. Sometimes this is accredited to Middlebrook. They think Middlebrook did state space averaging, but Middlebrook was just Chuk's advisor. And they were both Caltech people. That's what the little asterisk means on this slide here, that this is someone who went to Caltech. And the reason they started doing state space averaging there was because they were building converters, and the converters were going unstable when they put them into systems. So this was the very dawn of switching power supplies, and there was no theory that could make them work, that worked in regular circuit theory. So they had to come up with a new mathematical approach, and that was Chuk's dissertation. And here it is. There's a link here. So throughout this presentation, there are links. On the previous slide, there's a link to our cartoon series that you might enjoy. We ran that for a couple of years during COVID. And here's a link to Chuk's dissertation that you'll find online. It's in the Caltech thesis library. So anytime you see a block of text in the PDF that you should have downloaded, you will see there are links there for you to go and read. So there's a lot of homework for you if you want to do that. Students, if you're in control theory, I would advise you to go do some of the reading, and you will learn so much from it. So what Chuk's work was, it was very much equation-based and matrix-based and state space averaging. And he generated equations, and from those equations, he then generated the curves or the Bode plots, because it doesn't matter how hard you look at an equation, second order, third order. In Chuk's case, he went up to fourth order equations, which was his Chuk converter. Immediately for the engineering brain to understand that, it wants to look at a curve, and that's the Bode plot of the system. So his state space averaging did that for us in 1976 and generated the equations, and then the equations were plotted on curves. And at the same time, because Middlebrook was involved, he was very much a circuits person. He insisted, I think it was probably him that did this, he insisted that there be an equivalent circuit model to go with the state space averaging, so that the engineers could see a circuit, that you can envision what a circuit does immediately without having to look at the equations. So that was going on. And this all started at Caltech. And for me, this all started when my first day at work. That was in 1981 in Prime Computer. My office mate put Chuk's dissertation on my desk, and he said, okay, go read this for a week and then tell me what's going on in here. And I thought that was a test. But in hindsight, I realized he didn't understand it, and he wanted me to explain it to him. So it was probably both, actually. But at the time, I loved doing this. This was great. I could understand it. It's quite hard to go through. It's quite difficult to see how the right-off plane zeros come out, how the control curves come out of this. But once you got it, it was fun. And I assumed everybody was using that in the industry. Probably in hindsight now, I would say maybe 2% of the industry was actually using it, because they didn't have time. They were trying to build circuits, and you couldn't see how to apply it to all of the circuits that you built. But there it was. At the same time, this is state space averaging. If you like dealing with large matrices, and the matrices consist of symbolic elements. This is a matrix we'll see a little later in the presentation here with average power converters, which is a large order matrix in this case. And then what you have to do in state space averaging is you have to take the SI minus A inverse matrix and invert that by hand to generate all the equations that you're going to need for the converter. So this was tough work, but if you just come out of college, it's like, oh, I can invert that matrix. That's no problem. So that was going on that kept us all going and with equations and curves for a while. The one flaw in Chuck's approach was that it averaged all the states as well as averaging the switching function of the converter. And it turned out later on that you don't need to do that. So it was much more complex than it needed to be. But of course, that's easier to see in hindsight. Nobody could see it at the time. So there we go. So we had Chuck generating equations and curves. At the same time, or just a little bit later, 1980, I guess it was, Vince Bello, he was an industry person. He came out with an average circuit model. And you will find this in the 1980 Unitrode handbooks of the day. I think you can still go find those on the TI website. His work was actually, there was some of that being done by Gene Wester at Caltech as well, where you could actually just draw a little circuit, fill in the elements of the circuit, skip the equations altogether, and go straight to the curves of a converter. And Unitrode always did a good job of having their finger on the pulse of the industry. They gave people what they needed to get the job done. And what they needed was a quick way to do it with this average circuit model. So I would say the red approach here from Bello's circuit model was used by more than 90% of the industry. Maybe 2% of them went through state space averaging, and then the rest of them just, well, they said, well, we'll leave control up to somebody else. What did Bello's circuit model look like? Well, it had a buck circuit and a boost and a buck boost, and in there it put a little averaged circuit element, a 3-terminal element. And then from the element, you had to write the equations of the circuit itself. Or you could just give this to Spice. I don't know what the Spice of the day was, P-Spice or Intersoft Spice or something like that, which would plot the transfer functions of the converter for you. So this is the little diagram that you will find in the Unitrode handbook. So really quite useful to people, and it's going to come up again a little bit later. All right, so Chuck had his method going through equations and curves. That became the favorite, of course, the universities. Everybody I know at Virginia Tech, when I went there, we went through state space averaging to get the equations, which were mandatory. And then we went to the curves. We kind of ignored Bello. It's like, okay, that's for people that don't understand what's going on. But, it really was the more practical approach. Then along came Volperian with his switch model in 1986. So 10 years after Chuck's dissertation. And Volperian came out with the switch model. Now, Volperian was a student of Chuck's and Middlebrooks. And then you had Gene Wester and Richard Tomersky, both the little asterisks, who were involved in this kind of work as well for the switch model, that gave a different way to get to the equations that didn't involve matrices at all. And it didn't involve averaging all the states. So it made the analysis of converters so much easier. And then from that day forward, nobody at Virginia Tech ever did state space averaging again, including me. So I had done state space averaging with great enthusiasm before that. And then when Volperian did his work, it's like, oh, we didn't need to be doing that. And I have to show this slide like this because still today in most universities, as you go study state space averaging, which was very useful for its time, but it's not something that you should be using anymore. So professors out there, hopefully you can move on to a more intuitive approach that your students will enjoy much more, and go with the Vulperian switch model. So it used to get the equations. Vulperian switch model could also go straight to curves. You didn't need to go through the maths. You could do the same thing that Bellow did with his models and go straight from a little equivalent circuit to the curves. And when that happened, there was no need for anyone to use Vince Bellow's model anymore. I don't think people coming into the field these days are even aware that Vince Bellow was doing what he did. So that was just kind of a fill-in way of doing it for 6 years. And then, of course, I got involved in this thing. I did a current mode model. I could never have done this without Vulperian switch model. So I did the current mode model that went straight to equations, or it went straight to curves. And if you want to read that, there's a free book here. It's 200 pages on current mode control. Everything you need to know about current mode control for converters is in that book. So this was all back in the 1980s. Nothing much has happened in PWM converter analysis since then, to be honest. I mean, I get a little bit dismayed when I see yet another analysis of a voltage mode buck converter being churned out by the universities. It's like, okay, there's lots of other fun things that really need to be done in our industry, but definitely not that. What did Vulperian do that was different? Well, he had the buck and the boost and the flyback, just like Vince Bellow did and Unitro did. He had his little model in the buck converter, which looked exactly the same as what Vince Bellow was doing. But then his model in the boost, well, he took the same 3-terminal device here and rotated it on its side. Instead of doing a different device, which is what Bellow and Unitro did, he just turned it on its side. And then he did that again for the flyback converter. So he saw this switch rotation coming into play. And actually, Richard Demirsky had seen that for his work on amplifiers at the time. He was working on switch mode amplifiers and trying to do flyback switch mode amplifiers and boost switch mode amplifiers and trying to find the distortion. So he had actually found this rotation of the switch. So there's a big team effort going on here. But what Vulperian did, he said, hey, look, this is one invariant model. Every converter looks the same. You don't need to do state space averaging for the buck and the boost and the flyback and the chook and the CPIC and the zeta and everything else comes along. You only need to analyze this one little element in the middle. It's like analyzing a transistor. You only need to do it once for the transistor, not for every circuit that it goes into. So that was the genius of what Vulperian brought to us. So he just applied analysis to this little 2-port model here, a couple of scalar equations, and he had done the same thing as state space averaging. Okay, enough of that. So that's equations. For all you students, professors out there, if you need to generate equations, please do it the easy way. Don't do it the state space averaging way. Do it the easy way so you stay in touch with circuits. But now we're going to talk about, okay, where do equations feature in our life as designers of power supplies? So you've got different ways to plot transfer functions. One is the analytical expressions that come out of state space averaging of the switch model. The second way to do it is with the average circuit models. So that'll be the one that Vince Bellow gave us, or Vulperian gave us another flavor later on, or even Middlebrook gave us his canonical circuit model early on. So you can just run with those if you prefer and not do the analysis. And then you can do a swept simulation, which has only become really viable for most people, in the last few years as LT Spice has gotten faster, computers have gotten faster, and models have gotten better. So we'll talk about what that is. And then we have measurements. Now, if you're in the theoretical world, the university world, your life is all about the analytical expressions, and you love those. When you've been in industry for a long time, measurements, it's where it's at. It's the only real truth of the converter. And I can't emphasize that enough for people just getting into power electronics. If you're spending a lot of time on analysis, please try to emerge from your university career knowing how to measure circuits. And we're going to see why that's important in just a little while. But when you get into industry, that's what you need. So please try to learn that skill while you're at university rather than being so analytically focused. And I know you have to do that because you've got papers to write, and that's what drives the whole system. So, analytical expressions, isolated buck family. Let's start with a set of analytical expressions. Here they are. Here's the buck. And you can find these expressions in any textbook on power electronics. So it looks like a second order transfer function. There's an L and a C. There's primary resistance, secondary resistance. There's the output load in here, and there's diode resistance. You can add as many parasitics as you like to the expression. And of course, every time you add one, it gets more and more complicated. So let's the problem you run into with this is that you can only do an analytical expression on a converter if somebody has done the analysis for your system. And you'd be surprised, most converters that get built, they're not that simple. Somebody's added a little quirk to it, or there's a parasitic in there that's not being accounted for. So you can't find the analysis for exactly what you're doing. You can only find it for the very base level converters. So you can do it yourself. If you're a student, you think there's a new problem that needs to be solved, go ahead and do it yourself. And then the next thing you run into with analytical models is that you'll find that there are discrepancies in all the publications. Some people put in these expressions for Q, some people put these extra resistances in, some people does it this way. Everybody seems to have different notation, ways of doing the notations. So this will drive you really nuts, trying to reconcile what R sub L is for this author, what R sub L is for that author. There'll be big R's, little r's, capital L's, small l's, ESR instead of C. Everybody has a different thing. There's no standards in this. So, read any book you like, find any expression you like. You can pull it out of software if you want, which is where this comes from, and then do the analysis. And ultimately, as engineers, what do we want to see? We want to see the curve. So here's a power supply transfer function for a buck type converter. It's got an LC filter here with a little peak on it. It's got a -2 slope for a while, then a -1 slope when the ESR 0 kicks in. And characteristics of this little thing, it's got peaking here in this transfer function of 25.7 dB. So that tells you the Q of it. How do we generate this curve? We generate it with our software. So inside the software, you click on the loop.
You are using voltage mode control.
And then here is that transfer function. Okay. If you want the expressions, you go to the power stage, click on equations. There's your expressions that are in the presentation. So the beauty of having the equations is I can quickly parameter shift. So I can increase inductance, for example, and I can watch my transfer function move. So you can have a live, living, breathing transfer function instead of kind of a dry textbook type thing. Okay, take that back to where it was. So here we can see this, and this is people like students say to me, "Hey, can we get your equations?" It's like, well, why do you want them? Well, I want to put them in MathCAD. What are you going to do in MathCAD? Well, I want to move the parameters. Okay, fair enough. We can give you the expressions if you want those, and of course it's in the presentation. So that's fun. We can go to minimum line and watch the gain change. We can go to maximum line and watch the gain change. We can change the C. We can change any parameter that we want to in here. So that's the fun of having the expressions. I'm just taking it back to the original condition here. Okay, right there, 48 volts in the button. Okay, So that's how we work if you're lucky enough to have the expressions for your converter. 90% of the time for your converter in the lab, you won't have anything like an exact expression for it. So let's go back to our presentation. All right, but there you go, you come up with that. That's what we get out of our software here. Then you say, okay, well, I don't have an equation, all right? I want to do it the next level of abstraction from the hard analysis. I want to use something like Vulperian's switch model, or Bellows model, or Unitro's model, or whoever's circuit model that you want to use. So inside here is Vulperian's little switch model, and you want to measure the transfer function on this circuit. So it's a bit more real world now. We can see the output cap value, we can see the inductor value, and we see this running right here. So now the advantage to going to that, let's go into LT Spice, which is what we're going to use now. We say, okay, give me my small signal model. Here it is. Here's the 22 microhenries, the 400 microfarads, and you say, okay, I want to see the transfer function on this. So you click run, and it's done. So the beauty of small signal, very, very fast. Okay, now you add the trace, and you say, okay, I want to see B divided by C, which is my control function right there. And there is my transfer function in here. I don't want to change this to get the, oh, sorry, this is current mode. Didn't mean to do that. Should have been a voltage mode. Okay, so let me ignore that for now. Let me go back into here. Sorry about this. Generate the model
Creating
again.
LT Spice schematics.
Let's open up that file again. Small signal. Now we're in voltage mode. Let's plot it. So we add traces, B slash C. And there we've got our transfer function coming from the small signal model. So I'm not working as hard as deriving the equations or trying to find the equations. And trust me, that's a hard process, finding the equations. And lots of people just give up on this. They say, okay, I can't find it. However, you do still have a problem that somebody needs to know how to generate this small signal model. So now you go digging into the literature, and you say, okay, this is how I generate the small signal model for the converter. This is how I'm going to run the simulation, but there's a lot of legwork there for you. Of course, if you got our software, automated. Don't worry about it. One of the good reasons to get the software if you're in industry. But digging out the small signal model, or if you like the original canonical model from Middlebrook, you've got to get to a level of understanding before you can plot anything. So more understanding is needed, but it's a lot faster than writing the equations from scratch. Okay, but we get this instantaneous simulation, and hopefully the peak on this is 25.8 dB here. The analytical expressions, I think, gave us 25.9 dB, so that's like a 1% variation there. That's just numerical. So the small signal model that's generated here, it's the same thing that's used to derive the equations. So we would expect that to agree. And again, you need to know how to build this circuit, and beware once you go digging into this, and again, this will drive you nuts, that there are so many different average circuit models. When Vulperian did his work in a sensible world, everybody said, hey, that's great, let's all do it that way. But the world doesn't work that way. Everybody wants to do their own average circuit model. So you've got to pick and choose amongst a dozen of those to see which one works for you. So that's complication in your life that you don't really need. Okay. The next way of attacking it is the swept simulation. It's like, okay, I'm going to build this switching model in LT Spice because I want to see my converter waveforms. I want to see the switch current, the inductor current, the capacitor current that's flowing. I want to see the error voltage flowing. So you build this model in LT-Spice and you say to LT-Spice, hey, let's just sweep that. Let's sweep that with a simulated frequency response analyzer. So let's go ahead and do that. It's going to be a little bit slower now. So we pull in the model. We want the transient sweep model, which is right here. Okay, so here's my 2-switch forward. All the parameters are in there as we set them up. This is the circuit I have to build anyway to see the waveforms. So the question is, can I run this circuit as a frequency response with a frequency response analyzer? And can I do that in a reasonable amount of time? Well, let's try it. Click run, and off it goes. And now you can see it. All right, so it's generating a swept sine into the circuit. And this is actually the output of the loop, and this is the input of the loop. So you'll see the signal on each frequency. The frequency is increasing. This is working just like a frequency response analyzer would in the real world. So this signal is going to decay in size. And then this signal here is going to grow because the gain of the loop is the ratio of those two signals. So they're going to start shifting their amplitude with respect to each other. Okay. So there are other ways to do this. I know LT builds in their own frequency response analyzer now, but they don't do what we do, which is showing you both of these signals, which gives you intuitive insight to how a frequency response analyzer works in the real world. So I do encourage you to try this. And you can see we've done 24 runs out of 39. The speed of this, yeah, some people get upset, well, that's too slow. It's like, well, this is way, way faster than you having to generate a small signal model or you having to go find those equations, which may not exist, which means you have to go derive those equations. Okay, so we're sweeping through this model here. We're almost done, 33. Now, don't try this with complex models for your FETs and complex models for your controllers and complex models for your transformer. The more complexity you put in, especially in the semiconductors, the slower this will run. So you start establishing the fact that you've got to have different levels of your simulation models to make this all work. All right, it's all finished. You have to do some little things here to get the plot. Go to the SPICE output log, and this is all in our app notes, of course. And you generate the Bodie plot here, and then you say, give me a trace. Just before, like before, we want B divided by C. And there we go. So now we've got another way to generate this transfer function. And it didn't require any understanding of analysis to get the analytical expressions, and it doesn't require the small signal model. You're just running it on any large signal circuit that you can find. Even if you don't have any model to solve for your circuit, you can actually run it in LT-Spice and sweep the loop. So this is really nice. So we did that, and it took about a minute in LT-Spice. You can wait a minute, because you're learning about loop injection at the same time, which will be useful to you. So here's the swept simulation model. And now see that our peak has come down a little bit. It's 25 dB instead of, I think, 25.9. So there's only a 10% variation. So it's pretty close. So that looks pretty good. 3 ways now of generating the transfer function. And then we'll go back to our software. And we're going to do it the 4th way, which is, oops, it's not behaving, sorry. Too many things open here. Let's close LT-Spice. Let's bring up a frequency response analyzer now. Okay, so move my camera here. This works. Show you we have hardware on the bench here. we're getting ready to measure this circuit. Never trust presenters that don't show you some hardware. There should always be hardware running to keep the world real. Great. All right, so now we're in here, and we're going to sweep the actual loop.
Sweep initiated.
So now we're doing the exact same thing that LT Splice was doing, which is injecting a signal into the loop, but now we're injecting into the hardware. So you can see the count of the sweep here. And it's going along. It's always a little bit noisy down at low frequencies, but the phase scale, notice that's only a 1 degree phase scale. So that's actually quite clean. And we can see our loop, not our loop, this is our power stage transfer function coming in for the converter. And it's sweeping along. We see the LC filter coming in right there. A little bit of noise on it, but that's okay. Something you get used to after a while in sweeping power supplies. It's always going to be noise. And
phase
now,
margin is less than 50 degrees.
And now we go back. Sorry. Go back into
You are using voltage mode control.
And here is the predicted on top of the measured. It's like, uh-oh, things are not working as well as we expected at this point. So down at DC, yep, DC gain is good. Down at high frequencies, yep, everything looks pretty good there. When I see this noise in a paper or an app note, I'm happy because I know that's somebody that went and measured their loop. When I see little glitches in there, I say, okay, this is not just theory, this is somebody who did some hardware. So that always makes me happy. So what's going on here? You know, the peak of that measurement, well, it doesn't peak at all. So the Q of that filter is not what we expected it to be. So we did the SWEP simulation with 25 dB. Then we go to real world measurement. And the real world measurement is 19 dB. So we're 6 dB off in terms of predicting the transfer function. So I don't know if I can, would anybody in the questions or comments like to hazard a guess as to why it's so much more damped than we expect? Sorry, just trying to move my screens here. Got a lot of screens going. So why is this so much more damped than we're seeing in the real circuit? Okay, no one's guessing yet. But, you're waiting for the answer, I suppose. So we've done 4 levels here. We've done the equations. We simulated the small signal model. We simulated the large signal model. And then we did the real world measurements. And it kind of said, well, only one is correct. The real world measurement is correct. So that gives us a dilemma. What should we do? If you're working for a very fastidious, you know, professor theoretical type, they're going to say, well, we need better models. The industry needs better models. So you go away and you do a dissertation on damping it a little better. That's great. If you're in industry, it's like, you know, we got to ship this product. Let's just go with a measurement. Let's get it out the door. That is reality. So students, again, pay attention to this. You cannot get reality through your equations. Okay? It's too hard work. And anything you do to make it more sophisticated is going to make it even harder work. All right, so you've got to keep this foot between, I'm going to measure it, I'm going to predict it, try to bring them together, but measurement always wins. Maybe I could go back to my SWEP simulation circuit here and add some parasitics to the circuit. Well, the obvious parasitic to add, and we do this in our lab, is like, well, if I add a really big ESR in here, it will dampen. But that's a fake damping. If I add a big ESR for the cap, that will dampen. If I add a big ESR for the switches and the diode and the transformers, it's fake damping. And that's just massaging the transfer functions to make them look the same. You might cheat like that at work a little bit to stop somebody from bugging you. about your theory and measurement not matching. What I did in this circuit is I said, okay, well, let's put in the leakage inductance of the transformer. Okay, so this is only 2 microhenries compared to 20 microhenries here. That's going to get reflected up a little bit in here. So I'm only adding about a 10% increment in here by putting the leakage in here. But I'm sweeping the transfer function of this circuit with some leakage. And typically in our labs, when we build these circuits, we see 1 to 2 microhenries. Sometimes people will do better than that. And when we add the leakage to the circuit, I get this. Now we're pretty close to reality. All right. So I knew that adding leakage was going to do that. This is not intuitive to anybody that hasn't worked on this. So how did I know that leakage was going to do that? What, why? The question is why? Why does leakage dampen the resonance of the circuit? Because that's not all apparent. It's all apparent. It looks like leakage just adds to the actual inductance, and that shouldn't have any effect on the resonating of the circuit. So good luck analyzing this. Students here looking for a topic, why does my leakage affect the resonance? You can write a nice master's or a PhD dissertation on analyzing this circuit. I don't know how you will do it, to be honest, to get there, but this is a nice effect to show that, hey, I can get measurement agreeing if I put the leakage in there. Well, how did I know not to add leakage rather than a capacitance on the FETs or a capacitance on this or some real parameters for the FETs? How did I know that leakage was going to be the trick? Well, that came from some work we did a long time ago, January 1992. We did the analysis of the phase-shifted full bridge converter. And one of the characteristics of the phase-shifted full bridge is that it has a big primary leakage. And that primary leakage delays the turn on of the device. You've got to ramp up the current until it hits the load current, and then you're switching. So then you see the duty cycle. So the bigger the current, the more it rubs away from the duty cycle. So in the phase-shifted bridge, there's an inherent current feedback, just a little bit, and that little bit of current feedback drastically damps the LC filter characteristic in the phase-shifted bridge. So that's how I knew the same thing was going to happen in the 2-switch forward. So back then, if you go read that paper, you can read the analysis that we did to do that. It's not pleasant. It's approximate, but it did show you how this was done. I don't talk much about this paper anymore. In fact, I had to go dig it out. It's not on our website yet. I will put it on our website. But I don't talk about it much because if you're doing a phase-shifted full bridge converter, you're not going to do voltage mode control. So when you do current mode control, of course, it damps out the Q, and then it doesn't really matter. So in terms of importance to the industry, running the phase-shifted full bridge in current mode voltage mode control is not. It's going to be current mode for just about everybody that's out there. Did I ever do the analysis of this applied to the 2-switch forward? No, I didn't. I mean, the first time I ever did the simulation of this one with leakage actually was preparing for this webinar. This is a lot of fun to do. Try this SWEP simulation here. I had intuition, hey, the leakage is going to fix the damping. Put it in there. Oh, there it was. That would have been months and months and months of analysis if I could even get there. Probably at this point, I couldn't. By the way, there's a comment there that these switches and diodes, we put these in as ideal elements. You can do what you like, of course. You can put in a real model here for the FET. You'll slow it down maybe a factor of 4 if you do that. The more complex you get with your models, the slower it will run. And any semiconductor companies listening out there, we do not want a transistor device level model of your FET, of your control chip. We want behavioral models. Otherwise, the simulation is just appalling speed. So there we go. So hopefully that's given you a clue of what everything's about. with analysis versus other ways of getting the transfer functions. And again, I can't emphasize this enough. Measurement is king. And I had to learn this the hard way when I came into the industry. I was full of analysis and full state feedback and pole placement techniques and all the things that we did in university. And then when I went to work, everybody looked at me like I was from another planet, which I suppose I was. And they said, well, we just measure body plots. And then I would ask, well, where do you want the pole placement to be? Because the professor always told us that. And they said, I don't know. We just want low output impedance. We want a voltage source. And I thought, well, okay, we're going to teach them modern control theory here, do it the modern way. 6 months later, I was measuring body plots along with everybody else. That is the way. I'm sorry, but it's always going to be that way. All right, separate topic. 15 minutes to do this, so we'll do the highlights of multiphase. Multiphase is really important, and it's been really important for a long, long time. This is my dissertation from 1986, and there's a link here to it. You can now go see this online for the first time. I dug this out, scanned it, and PDF viewers are much better now that they did a good job of scanning. And it took parallel modules with the control module. Said, hey, what happens if you control them all with the same signal and then you feed one load with multi-phase modules? This was originally done back in the 1980s for emitter coupled logic for IBM, and they needed up to 7,000 amps at 0.3 or 0.7 volts. So 40 years ago, the demands were actually much higher than they are today on processors. Today, they only need 1,000, 2,000 amps. That's like nothing at these voltage levels. The other thing we did that was kind of unique is that we had 380 volts coming into a phase-shifted full bridge to give you that 7,000 amps directly. There was none of this intermediate bus stuff and then a point of load converter. This was done with a great big bulk supply. Fairly close to the CPU, but very similar to what we're doing today. What's cool about these converters? Well, you can run multi-phase converters. I don't care the topology. This can be 2 switch forwards, it can be flybacks, it can be boosts, it can be phase shifted bridges, it can be LLCs, anything you want. But if we're doing a hard switch converter like the 2 switch forward, we can choose to switch 3 modules at the same time here. That's with the current synchronized. And then we can do the synchronization and phase shifting from module 1, module 2, module 3. And when we do that, you see we knock down the peak of this current. This is the input current signal here. It's knocked down by a factor of 3, and the frequency has gone up a factor of 3. So in terms of size reduction, we've got a 9 times improvement of the demands on the filter that has to be built. 3 times the frequency, 1/3 the amplitude. This is so much easier to filter, and this is on the input. On the output, it's even more profound. So here's a 4-phase converter simulated in LT-Spice. And again, this drops right out of the way we do this. We talk to LT-Spice directly and feed it the phase-shifted converter. So here's the ripple current in one phase, which is about 2 amps peak to peak. If I took all 4 phases and slammed them in parallel with each other, that would be 8 amps peak to peak. But when they get summed out of phase into the capacitor, it looks like this. It's about 1/10 of an amp going through that output capacitor of the converter. So this is the power of the multi-phase system. And it's the only way they ever got those processor power supplies on the motherboard. There's no way you can do hundreds of amps with a remote supply in that high density environment. So multi-phase is crucial, but it's been around for a long, long time. Analysis of this, well, this was fun to look at historically. Please don't go read this and take it seriously. Okay, don't do this again. We had to build up a kth order matrix for the K parallel modules that you have and try to derive the transfer function, because we didn't really know how it was going to affect the design of the control loop that we had here. So what did we come up with? Well, even though there are K modules in there, it's a second order system. I would modify that these days and say it's a third order system because it's current mode, but at that time we didn't have that insight available. The equivalent L of the circuit is the actual L of each power stage divided by K. That's the number of stages. And the gain goes up with the number of phases. So the more phases you put feeding the cap, controlled by the same current, put 2 phases in there, you've doubled the gain. 4 phases in there, you go 4 times the gain. So in terms of doing the control loop, it's really pretty trivial in here. So here's my controller for a single phase, and you see it's got a 3K and a 2K divider resistor in this particular case. When it goes onto the 4 phase, this resistor gets multiplied by 4. That's the number of phases. This resistor gets multiplied by 4. The other compensation components are the same. So the design of the loop is actually trivial. Just be aware the power stage gain has gone up by 4. The controller gain has to go down by that same factor of 4 to get the same loop stability as you had before. So that's the interesting part of the multi-phase. Took us a long time to get there, 2 years of work of my life. And then of course the output ripple drastically reduce. You know, that's huge. That's huge for any power system you're building. So look at the multi-phase. Big advantage of this multi-phase, well, your converter size is hugely reduced, and there's lots of factors working for you here. One is every stage is lower power, so every one can run at a higher frequency. Now, it doesn't exactly scale with the number of phases because you kind of run into a curve that slows you down. But you can at least double the density of your converter by running the phases at different frequencies. And then you can have a smaller inductor. You let there be more ripple in the inductor because they're all going to cancel each other out by the time they hit the output cap. So there's another 2 times gain in the inductor. You got distributed semiconductor heat losses. Instead of one great big synchronous rectifier, you got to slap a heat sink on it because you can't get the heat out. Suddenly you've got 8 of these, or 4 of these, and 4 of those there, and you've distributed it over the board. You probably won't need a heat sink. So you're going to get a lot more gain there. As soon as that heat sink goes, boom, density goes way up. And then, of course, the big one is the output cap is at least 10 times smaller, I would say, when you go multi-phase. Even if it's just 2 phases, you're probably going to get a 10 times reduction on the output cap. And I don't list the input cap here, but of course the input filter is also going to scale down. You know, probably I hesitate 10 times smaller there as well, because the input filter is still dealing with the high frequency edges, and that's what tends to determine the input filters. But you will see more improvement there as well. All right, I was planning on doing much more in this presentation, but enough already. Here's the other things, students out there, for you to look at, or even industry people. Output filter analysis. When I did the multi-phase, I also did the second order filter. There's a link there. Please go read that. If you're looking at input filters, we've got lots of videos and topics on input filter coming from Middlebrook's original input filter problem here. So there's a nice video you can link to there to watch that. TL431, I hate doing presentations on this because I don't like it. It's just reality, but as a control purist point of view, it's a horrible device, but the reality is lots and lots of people use it. And it's a horrible device in that you're running off the parasitics of the device. You're gain limited on things, you're range limited. The optocoupler becomes part of the transfer function. I don't like that, but you know, we've got the analysis for it. You can go click on that too. And then there's one more paper that you might go look at. And this is 6 common reasons for power supply instability. Have nothing to do with the loop gain. Okay, it's all to do with noise in the system. So when somebody comes into us with a power supply, they say, hey, we want to measure the loop. Very often we will spend a day or two cleaning it up before we can even measure that loop. So the apparent instability, it will look like an oscillation. It will look like subharmonic oscillation, but it's not. It's something else. So I do suggest you read that because everybody deals with that kind of issue. And then multiple output converters. I don't have a link here. None of us talk about multiple output converters because they don't behave. But I could do an entire presentation for a day actually on multiple output converters and the variations that we see inside them. The weirdest one I ever saw was where the ESR of the output diode determined the stability of the entire converter. Right? I never wrote that up because it was a strange case, but strange cases are often relate to multiple output converters. Okay, that's my presentation. We're almost at the end here. We're going to take some questions now from you. Just be aware we have software around. If you want a demo of this, send us an email. You can get that. We run workshops. September is full, December is filling up, and October in Europe. We're still taking people to register for that. And you will learn much more of our techniques when you come to those workshops. And frequency response analyzers, we have a range of those for doing the measurements. It's a buyer's market right now for frequency response analyzers. There's so many available. Okay, we offer the full featured ones here that do everything for you. So think about that. We have our Facebook. Oh, I'm sorry, the Design Center on our webpage. Okay, there's over 150 papers and videos in here to go learn from. So some great stuff in there for the students, whoever. It's all free. And then there's our Facebook group. We got almost 8,000 members now who ask hard questions about their converter not working properly. So go take a look at come join our Facebook group. There's a lot going on there. And let me pull up the questions now. So thank you for all paying attention. It's the end of the formal presentation part. I can't see any questions. Oh, there we go. There's my questions. All right, there we go. How do I recommend stability of multi-phase systems with digital control? You're gonna measure loops. It's still the way that we do things. Or you hope maybe you have a digital controller that can measure its own loop, but to get to the understanding, it's still a loop measurement. You can send me an email with question regarding Volparian's method. Absolutely, please do that. The slides should be available to download for you. Okay, so if you go click on the little paperclip right here with materials, that gives you the slides. Okay, but we can always send them out to you. Will I do a presentation on multiple output converters? Well, there'll be a survey afterwards. What topic would you like? Multiple output? Yep, it's another one in there. Magnetic isolated op amps. There are so many different ways of analyzing the feedback. There are so many different ways now, really good ways of doing the isolation. You don't have to use the TL431 and optocoupler anymore. So that is going away for many people. Beat frequencies from interleaved, unbalanced, yeah, all kinds of things. So when you current share, things can go wrong. Anytime you go more complexity, another effect comes in. So I don't understand the ripple current question there, so I'll skip that one. The capacitor current is the combination of the output capacitors. The 4 modules are separate output capacitors. Well, there's 2 ways to have modules together. You can have a power supply with its output cap, and then bring another one with its output cap. So then, of course, you double the output capacitance, and then, of course, the gain doesn't go up. But if you've got one fixed cap and you say, I want to feed it with one module, then another that doesn't have a cap, you can go either way or a little bit of each one. workshop in the European Union. Well, let us know which country you like. Yeah, we're certainly interested in doing that. We've done it before. We've done France, we've done Italy, we've done Germany. Um, it's hard for you to travel to the UK, but it's hard for us to take things into Europe right now. We have to drive all of our equipment into across the channel and hope that they let us in every time. But yeah, we can do it in the European Union. In general, the reason we choose the UK is because it's cheap to fly there. So everybody is okay with going into Europe except for the visa issue, but you should be able to overcome that for coming in for educational. Can we do loop game plots, digital control using frequency response analyzer? Probably. I'd have to see your schematic to answer that, but normally you can get at the loop game. Simulation files, you get all these sim files when you get RidleyWorks. There are student versions available. Average models are the same as we do it traditionally. What does that mean? Well, you can write the equations if you want to. I don't know why you'd want to do that. State space is used in nonlinear controller design. Well, every controller is nonlinear. A PWM converter is nonlinear. If you like doing state space, do some state space. If you're in university, sure, enjoy your state space. There's other ways to do it. I like to keep things simple because you've got a converter to build. Why is the TL431 so popular? It is popular because it's a really good reference and an op amp at a really low price, and it's only 3 pins, so it looks really, really simple. Okay, that's the only reason. So if you tried to buy a reference, a precision reference, and an op amp separately and power it, it's going to cost you more than a TL431. So it exists in the bottom feeding power supplies out there. All right, so they prefer to use it. It's the only thing they can afford in general. Okay, Europe workshops, we got that. I should delete these as I go, shouldn't I? Sorry. What is ripple current rating of a capacitor? It depends. If you've got a multi-layer ceramic, have you got a film capacitor, have you got an electrolytic capacitor, you've got to do the hard work, I'm afraid, on reading the data sheets and finding what that ripple current is. Is it a good way to think of the leakage inductance damping the LC resonance? Yeah, no, the leakage inductance, the way it damps the resonance is it delays the turn on. You've got to ramp the current up before it's fully on. Okay, so you're losing some duty cycle with the added leakage in there. Okay, it's not going to make any difference to current mode control. It's only voltage mode control that's going to affect. And you should all be doing current mode anyway. Leakage can be treated as a loss factor just as a resistor. Well, that's kind of vague. You can call it all. We want numbers, okay? I don't want words like loss factor. Let's make it, a real thing. Active rectifiers, reasonable method to analyze a circuit. I don't know. When somebody comes to me with a circuit, here's a circuit. Okay, they say, hey, I want the analysis of this circuit. It's like, well, do you want the analysis, which will probably take us 2 years and cost you a fortune? Or do you want us to close this loop on you properly? Which means we're going to measure a loop on there. Because we want to get done fast, you want us to get done fast. Okay, so analysis of circuit, again, you've got to decide how deep do I want to go in the analysis? And as the topologies get more and more complex, the analysis gets more and more difficult. Estimation of the ESR of the output cap, that's all. Real world components of parasitic resistances. Well, we can actually take if we go into LT Spice and we do that transient sweep, you can take this transient circuit here. We've shown how you can include leakage, put that in there. We also, in one of our presentations on the website, we show you how you can actually put proximity loss in the primary, proximity loss in the secondary, core loss on the transformer, core loss on the inductor, proximity loss on the inductor. You can run all the transfer functions again. Nobody ever is going to do that analytically. It is simply intractable. You can't solve that problem analytically. And it wouldn't make any sense to try and do that. But you can put as many parasitics in there as you like. Okay. PCB parasitics, yep, that's all part of it. Resistance of the traces on the board, we run into that in our lab sometimes. If you don't measure in the right place, you don't get the right results. Analyzing the zero order sample. Well, we have something on our website that shows why you can't go above half the switching frequency. I was thinking of including that in this webinar, but it was too much to do that. But you cannot go above half the switching frequency because the phase margin will always go to zero at half the switching frequency. What kind of tools do I recommend for considering cross-regulation? Hardware. Build the hardware. Build the hardware. There is no getting around to that. Students out there, if you have access to labs and scopes and things now in the university, build hardware. Okay, when you go for your interview, they will talk to you about the hardware with great enthusiasm, and you should be able to do that too. If you want to talk about analysis, then you may or may not get that job. Okay, but this field is hardware. This is not an analytical research field. This is a hardware practical application field. I cannot emphasize that enough. What power electronics book do I recommend? All of them. Manictal is fine. That's good. I've got a book. Bulgarian's got a book. Should you read them? I don't know. Go start in our design center on our website. That's a really good place to begin. I'm not sure. The link is in our notes there, but we've got so many notes there. I would rather see you read those and try to plow your way through textbooks. You can see in my background here, there's a big pile of textbooks. Most of them are unopened, except to look at the pictures. Workshops in India? Probably not, but we are talking to people in other parts of the world about that. If you'd like us to bring a workshop to your country, then send us an email and you can help us with the logistics of getting that done. Art, if you could turn on your microphone, do you see any questions I haven't answered? ESR, ESL is off. If you want to put that into the swept circuit model, be my guest. Okay. LT-Spice might not like it, but you can certainly include that. Is it the tolerance of the parts on the Q? I'm sorry, I missed these comments at the time. No, it's not that. It's, as you saw, it was the leakage that causes that. Has a study been published indicating the trade-offs between these various models? No, it hasn't been published because IEEE would not be interested in such a publication because it's not theoretical, and it ends up with the conclusion that the only thing that really works is the measurement, which kind of goes against the role of the IEEE and research, It's like all models, all analytical techniques are by definition flawed and approximate. And you don't know how approximate they are until you go measure the circuit. Okay, so no, there's no comparison, there's no paper, there's no study. There's this, okay? So you got this. Go ahead and write that out for me. That would be nice. Skin effect, proximity effect, they do not exist in exclusion to each other. As soon as you have skin effect, you have proximity effect. It's all one thing. It's all one equation. The skin depth is part of proximity. And we have plenty of seminars, webinars recorded on our website where you can go see that. Have I seen issues with the placement of taping points in remote sense? Yes, I have. Everybody is different. So if we come and help you with this kind of thing, we're going to look at your circuit diagram, and then we're going to get into the remote sense, and then you get into the difficult part of, well, what is ground now? Is ground? So it can get very difficult for doing that. But yeah, we have strategies for the modeling this. Most of them involve making measurements. So make sure you are very proficient at making measurements. Are there plans to add inverting converters to RidleyWorks? No, we're full on. Just adding the things that we're doing. We're working so hard on it all the time. Everybody in the world bought a copy of RidleyWorks. Absolutely, we would make it do everything. Such is the world these days that everybody wants LT Spice because it's free. And so, you know, the more people buy it, the more we will put in there.
More questions at the top of the list, Ray.
There are. How to choose the switching frequency? Well, the higher the switching frequency, they're going to cross over at about 1/10 of the switching frequency. That will give you better loop response. So you're going to do current mode. That'll give you the best. Bump your switching frequency up, and then your crossover can go up as long as your op amp can keep up with it. How do I deal with manufacturing variation on stability? Well, inside LT Spice, you can put in the parameter variations and do sweep after sweep after sweep. You can do that in the equations. You can do it in the average model. You can do it in the swept model to do that. Well, our software has equations. They are deep inside there. Okay. So we put all the equations I know of inside our software. So do we rely on it exclusively? No, we then hook our software directly into our frequency response analyzer so you can pull in the reality. So of course we have equations in there. There are approximately 7,000 of them. So if you ask for them, be careful what you ask for there. I don't know what you would do with all that. You see any others I'm missing, John? Power supply design volume 1, will it be available again? Yes, it will. And we've been saying that for 6 years. We have to update it. We're going to make it a soft copy that's available. And the main hang up in there is changing all the reference to something active. And it's just such a big task that we didn't get around to it. Yes, it will be available. And hopefully volume 2 will come out, which will be magnetics. I keep starting to write it, but we get so busy doing all these things. Do you see any others, John?
No, nothing. I mean, there's bits and bobs lying around. I've got to say, I learned something today. That damping on the power stage gain due to leakage inductance. That was interesting.
You know what, John? I learned that too while I did the presentation. While I was preparing the presentation. It's like, you know, I've always thought the leakage was part of it because of that phase shifted full bridge, but it's the first time I tried it. So if you've got this little model here, right, you say, okay, I'm not getting the right transfer function out of it. How do we do that? Well, you just grab an inductor, stick it in there. You right click on it, 2 microhenries, done. Okay. Then you sweep the loop. You'll see the damping. This is so much fun to do. I'm having such a blast inside LT Spice, putting these new parasitics in there and sweeping the loop. If I had to analyze this from scratch, no, I'm not going to do that. Okay, but yeah, anybody that's got our software, you know, just take these LT Spice models, put the proximity in, put the core loss in, put leakage in, put your real FET in there with switching rise and fall times. You'll get the same effect out of that as well. Okay, you can get and you can move so much closer to the reality than you can get with the equations. So, you know, don't get hung up on the equation approach to this. I think we're control loop analysis of the LLC. Nowadays, just about everybody we see, all the hardware that we see. So this is an LLC in here. Okay, this is a very nice. I can't remember how many kilowatts this is. Oh, 1200 watts converter here. It's got PFC up front. That's the big L there. That's the big cap over there. And then this here is a 1200 watt LLC converter down to 12 volts. It's really amazing density and amazing efficiency in here. Okay, but I'm pretty sure they're using current mode there. Everyone's doing current mode. The LLC converters figured out current mode a while ago. It's not hard to sense it. You just got a little AC current sensing on the primary. Little transformer in there is doing that, and it works the best. You don't want to do voltage mode at level C anymore. Somebody asked about the coupling factor, mimic leakage inductors. Yeah, of course. So I don't do that because I have a coupling factor in LT Spicer of 1. And Art Nace kind of gave me that. He said, okay, build it as a coupling factor of 1, because if I give you a coupling factor of 0.99, then you got to figure out the explicit leakage. It's like, oh, that's too hard for me. All right. So I like to build a perfect transformer, then add the parasitic afterwards and see that leakage in the circuit. All right. If your manager doesn't like to see an inductor here in the primary because it doesn't physically exist on your production schematics, like, all right, we'll go change your coupling factor there. I don't know which one would simulate faster. They should theoretically be the same, but you're welcome to go and try that. Give us some feedback on the Facebook group. Facebook group. I think we're good, John. We've gone through most of these. Yep, you get a little survey after that of this. Please, slide 4. Yeah, I don't know. Go read the dissertation. Okay, I am so far removed from this dissertation. I am so far removed. I will never do SI minus A inverse again. Okay, it's not going to happen. But we didn't have singular matrices, and when you do the SI minus A, it's no longer singular, of course. So the SI minus, when you do SI, you know, industry people, you have no idea what I'm talking about because you forgot this. University people, please, if you find yourself digging into multiphase and you want to build on what we did with my master's dissertation, please call me, email me, whatever, to try and encourage you to do it in a different way, because I'd rather see you spend your time on the hardware of this. I was just talking with Jaron earlier today about, the complications of multiphase have nothing to do with the state space analysis. It's like, how are you going to do current sharing? What are the complications of doing this with digital control and the oscillations that kick in and the strange things that people want to do? That's where the real world is. Okay, I don't think you're doing any state space averaging to solve that problem, are you, John?
I can say certainly not.
So there you go. There's the real world approach from the world of Cisco for you. Okay, I think we're good here. Thank you, everybody, for paying attention. One thing is, we are considering very seriously doing a long-form educational webinar for about 3 or 4 hours, like a half-day webinar. We would include our software with it. We're going to price it around $99, so it's affordable and so on. And it will be, we'll slow things down and we'll go through examples and you can follow along. My thought is to do something like, compensation design. Everybody talks about that, but we'll show you how we do that in detail and not rush through it. So if you are interested in that, then please let us know. And of course, if you want to see, how to get this all done, in the real world, come along to one of our workshops where we do all of these techniques and you can learn it firsthand. Of course, meet many of your colleagues in the field doing all this. So thank you all. Thanks for paying attention. If you have follow-on questions, feel free to send them to us. And we will see you again at the next webinar that we do. Thank you.